compute these. And they have mathematical equivalents here, whether in summation or matrix notation, that are all implemented in our GraphPause library, which is available in many, many languages. And so this has been this sort of mathematical foundation, and it's all based on work in one of our books that we wrote that sort of lay the foundations for this. We've written a couple of books on this topic, and they really gave us the mathematical foundations for doing this analysis. So that's the tool that we use. So what does the processing pipeline actually look like? So we have our images, our sparse pictures of the entire internet celestial sphere, right? Those are just sparse images, and we analyze them with something called graph neural networks. And that's just a regular neural network, and a neural network is just a sequence of linear transformations with a nonlinear transformation between them. The math is not actually as complicated as people think. Just imagine a bunch of matrix multiplies, and every once in a while you do a threshold between those matrix multiplies. It's not that complicated. Graph neural network just means that instead of, say, looking at an image, we're putting in a graph and the features of the graph. And so with that, we can then do a bunch of these are essentially standard neural network steps for analyzing the data. And one of the things that's very different about what we do is mostly neural networks are used to categorize things. Like, I take a bunch of pictures from the internet and I want to find cats, right? And so I have a whole bunch of cats, dogs, cars, boats, chairs, astronomers, whatever. I have all these categories, and then I basically try and do categorization. Well, the internet is so dynamic that doesn't really work, right? There's new categories, there's been new categories that have been created in the time of this conversation, hundreds of them, and it's not really effective to do that. So what we did do that's a little different is that we use the neural network to come up with really, really good models of the normal background behavior, so that we can then see deviations from the background and explore those. And so we're kind of taking neural networks and twisting them on their head and saying, well, we have tons of background information. Why don't we just come up with a really, really precise model of the background and use our neural network to do that? This is Newton's method to do a two-parameter curve fit to the data. I could never say that to my fellow computer scientists. But if I say it's a graph neural network with all these steps, they get it, right? When I first just said, yeah, I'm just using Newton's method to find two parameters, they're like, I have no idea what you're talking about. But if I say I'm using graph neural network to do inference and train a model for the background, they're like, oh, I get it. There's a lot more people in the world who understand this statement than understand the statement that I made before.
So just to be clear, the sparse images are your 10 billion by 10 million matrices?
4 billion by 4 billion.
4 billion.
Yeah.
Wow.
But we're only recording if there's only like a few million actual non-zero entries that we have to store. We don't have. That's the whole point, right? Is it's mostly zeros, and we don't need to store those zeros.
Okay.
That's the whole basis of sparse matrix math. Is that you don't need to store the zeros because you know what happens if you multiply by 0, and you know what happens if you add a 0. So you never need to store zeros. So one of the things we discovered is that the window size that we use affects the quantities that we see. So here we're looking over time, right? And what we're saying is like, okay, in our window, what fraction, let's say I observed 1 million events, what fraction of 1 million is the unique sources that I see, right? And what you see here is as the window gets smaller, so this is like 100,000, and this is like 100 million, if the window is smaller, a greater fraction of unique sources will exist. So if I see 100,000, this is saying if I'm looking at 100,000 events here, I'm going to see about 100 unique sources. And then as I go up, that number increases, but the fraction goes down. And so this is a kind of very interesting way to look at the data, and what we discovered is that this obeys a simple scaling relation. So if I just look at the window size and scale it to about the power of 1/5, I can get all these curves to lay on top of each other. So that's a pretty interesting observation. And this is just with unique sources. we see it with unique sources, we see it with unique destinations, we see it with a maximum number of packets you've seen a link. We see essentially throughout these observations that there are nice empirical relationship that says, okay, if you go collect this many packets on the internet, I can tell you how many unique sources you'll see, how many unique destinations you'll see, how many, what link will have the maximum number of packets, like how much will be the brightest connection there. And so this was kind of allows us to now sort of properly normalize between different collection windows. It also makes, it's very powerful to make these predictions in advance. Like you can now tell someone, it's like, well, I collected this many things. Well, you should have seen this, this, and this. And if you don't see that, well, that's funny, that's weird. Like if you collected 1 billion packets and you only saw one source, you'd be like, that's really odd. I should have seen 10,000, right? And those are the kinds of very useful observations that we can use to understand the internet better. So another example that's really important is knowing where your detector is. This might seem like a relatively obvious thing, right? We know our telescopes are in Hawaii, and it's important that we know it's in Hawaii or Chile or whatever, right? Because that'll determine what time of day we can see certain things. Well, the vast majority of sensors on the internet are essentially placed. Person comes in with a box, then someone points into a closet, they open the closet, they look for a position that's empty, they stick it in, they find a cable, they unplug it, they stick it in, it lights up, it says, I'm getting data, they yell in the hall, are you all getting email and can browse the web? Yep, they leave. Well, although it will collect data and observe things, we don't actually know where we've plugged it in. And there's where we think we plugged it in based on what the network is doing, and then there's what it's actually doing. And so one of the big things that our capabilities that we developed is allow people to see that. So for instance here, we can take our traffic matrix and we can bucket it into various types of things. Like let's say we had a sensor that was on the boundary of an organization. And so we would, it's not to expect to see any internal traffic, we expect to see traffic on the boundary, and we wouldn't expect to see external to external traffic or external to internal traffic. And so we can now look at these billions of packets and do these statistics and say, all right, this is pretty good. We expected to see all the data in this sort of crosshair here, and we call this a focus sensor. We know where it is. It's mostly collecting what we want to do. And then there's these little bit of the outliers here. I mean, these are really small fractions, but those are probably things we should go check out. Like, we're expecting this to be 0 outside this crosshair, so we might want to go look at that and say, hey, what's going on here? And we might find a misconfigured printer or something like that. So this actually helps you make your network work better, right? As opposed to an unfocused sensor, where you can see, I have seen all kinds of data in everywhere where I'm not supposed to be. This is a sensor that's like completely misplaced. Like we don't really know what it is. You'd be surprised, like a significant fraction of network sensors look a lot more like this than this. And this is the first time we've been able to give people who run these sensors a tool where they can actually go and like, you can actually tell me like where my network sensor is, and you can tell me, because more importantly, like I think I installed it right at the beginning, but the network changed, and the network sensing people are always the last people to be told, right? It's like you get to build a telescope, but then they move the mountain, and they never tell you that they've moved the mountain, and you're like, the stars are in a different position than I thought. And then once you have this buckets, it's very important to look at the buckets differently. Like the statistics of external to boundary will be very different. These are just another, we can do this as sort of link brightness, how many packets are going over link. It's all power laws, it all obeys our power law models, but each of these buckets here has very different statistics. So like just the inbound versus the outbound statistics differ by a factor of 30. And so that was another thing. But after you get it focused, you then see you really need to look at the buckets in the right way so you can analyze them properly. Oh, and actually, as I said there, this is all heavy tail data. This is This is what a light tail distribution would look like. So if you fit a Gaussian to it, this would look like. Every single statistics course we've ever taught you is on light tail statistics. The first page, maybe there was this little thing that said, we will be studying, independent, identically distributed distributions that obey the central limit theorem. Central limit theorem means all moments exist. So that means I can integral x squared, x to the, all of those, I can integrate them and they will always return and, they will converge to a constant, some actual number. They won't diverge to infinity. With heavy tail distributions, you might have the 0th moment. This exponent is usually like -2, -1.5, so you can kind of integrate it once, but you have no higher order moments, which means the central limit theorem fails, which means your entire statistics textbook is out the door. Now, a colleague of mine, who's a professor at Caltech, has written the first quasi-accessible book on heavy tail statistics, i.e. accessible to undergraduate, advanced undergraduates and early graduate students in applied math at Caltech. So, but we have the first book out there on that. It's fascinating stuff. This stuff is not weird. Heavy tail statistics, everything to do with networks, everything to do with social media, almost everything to do with wealth distribution, everything to do with natural disasters. All of these really important topics are actually governed by heavy tail statistics, right? And we don't teach them. We don't really understand them that well, but it is a growing and a very important field. So here's just an example of what we can do. So this is essentially source brightness and the probability of seeing, of a source having that brightness. And we can now, this essentially is what we call a Zip-Mandelbrot distribution. It's essentially this particular form of heavy tail distribution. And with all our data, one of the things we can really do is get very precise estimates of these coefficients, right? And that's kind of the big difference from what we can do. Before, they basically say, well, it's kind of 2, right? Well, now we can say it's 2.01, and this offset is -0.833. And what's interesting, at a particular site, at a particular detector, these things don't change over years. They diverge a lot from site to site, but they are very, very constant at a particular site. And so we can now, make those more extended types of observations. An example, and we'll get into sort of the difference between our blue and red. One of the things we can do is cross-correlation, which is a really like we do cross-correlation statistics in astronomy all the time. In this case, it just means if I look at a particular window of data and I see a bunch of sources and then look at some later time, what's the probability that I will see that one of those sources again, right? It's very simple temporal correlation, right? And so in this case, we're doing cross-correlation between two sensors. We have a sensor Kada and what it sees, and we have a sensor gray noise. And we ask the question, well, at a given time, did they see the same things? And what we see here is we look at the Kada sources, which is many more, and we say what fraction of them are seen in gray noise. Gray noise is biased towards seeing very bright things. And as we can see, as the source gets brighter, the probability it will be seen by gray noise, essentially follows this very simple logarithmic relationship, which is sort of expected, right? This is for all sources. Interestingly, when you look at the red sources, the malicious traffic, it then drops off rather precipitously. Not surprising, the malicious sources does not want to be too bright, right? It does know that it should throttle itself to a certain degree, otherwise it's going to be too visible. So that's kind of the spatial correlation between different sensors. This is the temporal correlation. So within gray noise and Kada, we can ask the question, what's the likelihood if I observe something at a particular time and I wait a little bit longer, am I going to see that source again? And one of the really interesting things here, there's two interesting points here. The first is that we have another, if you can see here, all these sort of dotted lines, right, are 2-parameter fits to something called the modified Cauchy distribution. So we have a very, very nice empirical fit to these different observations. Just like we had the zip Mandelbrot distribution before, we have a very nice fit to this distribution. In addition, the second thing we see is the benign traffic, the correlation time, or the full width half maximum, right? A term that we all know and love here. The full width half maximum here is on the order of years for benign stuff, but for malicious stuff, it's extremely short, right? Now, and this is how we do science, right? We go and get some really good observations. We do a lot of hard work to make those observations very accurate and precise. We then fit, low-dimensional models to them, and then we ask, well, what's the underlying reason for this? Why could it be that it follows this curve so well, right? So before I get into that, what I've described so far is we have a pretty nice holistic background model of the entire internet. So given a window with NV observation, the probability of seeing a source emitting D packets being observed again at time t is proportional to this whole set of equations. So I can pretty much, wherever you put a sensor, I can make a prediction about what you expect to see and, given a particular observation time. And then all these parameters here are just parameters that are due to essentially the site and specific to the site and the detector. But once you've set them, they probably aren't going to change very much over time. So when we go back to that, so that's the overall sort of empirical formula. Let's get into sort of understanding this a little bit more. And so we want to explore this concept of a Cauchy distribution, right? I think a standard way we look for insight is like, well, what other things obey a Cauchy distribution? And sometimes it's called the Lorentz distribution, sometimes it's called the Britt-Wigner distribution. It's sort of a canonical heavy-tail distribution. In statistics classes, where they want to show you an example of a bad distribution that doesn't obey the central limit theorem, they bring out the Cauchy distributions. Like, this is really bad. You don't want, if you see things like this, just run away and pretend they don't exist, right? It's used to model stellar spectral line broadening. It's also used to model, but I don't think anything we have to do in the internet has to do with stellar spectral line broadening. I don't really know how to connect those two. It has to do with rainfall events. There's also a thing called Gull's lighthouse problem, which is really more of a, not so much a practical problem as a teaching example. And basically allows us to kind of develop some intuition about what this is, what's really going on here. And so let me sort of explore this Gull lighthouse problem a little bit more. So here's our basic Cauchy distribution, right? In this case, our unit tends to be time, but now it's going to be space. We're just going to convert x, it used to be time, it's now going to be a spatial coordinate. It kind of looks like a two-tailed normal distribution, but it is a heavy-tailed distribution. Like this drops off as x squared, which means you have no moments above, the second moment, basically. So again, they're heavy-tailed, and the Gull's lighthouse problem basically asks the question: if I have a lighthouse and I have a coastline, okay, what will be the distribution if this lighthouse is blinking? What is the distribution of light that I would see if I have detectors on the coastline? So basically, the lighthouse is spinning along, it's randomly emitting blinks, and you want to ask the question, well, what's the probability of me seeing a blink on if I have a detector anywhere on this coastline? And this will give you the Cauchy distribution. It's also not an entirely bad analogy in that that's sort of like our sources are like these randomly blinking, periodically randomly blinking lighthouses, and we have a coastline that we're observing from. So this isn't like the most strained analogy. So now then we can ask the question, excuse me, use animation, right? There. So we can then ask the question, okay, let's say I have a different coastline, right? So rather than a flat one. And there's an equation I can use to what we call the generalized Cauchy distribution. So the Cauchy distribution results from a flat coastline, but there's actually an equation you can use here and solve, and it will give you this kind of shape, right? So if you give me a coastline, I can give you a distribution. Now, there are, of course, constraints on the coastline, like on continuity and other types of things, but if it's sort of a nicely behaved coastline, I can actually compute what the distribution would be. So I can go from coastlines to distributions. Well, if I go from coastlines from distributions, can I go the other way? If I have a distribution, can I now invert and see what the coastline of the internet looks like? Like actually create a geometry for what this looks like. And the answer is we can, right? So unfortunately though, this particular differential equation, you might be like, well, can't you just solve for f, right? This is the probability and this is f is the shape of the coastline. Well, it's really, really unpleasant, differential equation. In fact, of course, the first thing I did is type in Wolfram alpha, and it like, just depending on how I wrote like certain things in numerator and numerator, the same equation, it gave me completely different results, right? Actually, I know Stephen Wolfram, like, Stephen, your software is broken, you can't solve this problem. So he didn't get back to me. But it's a very poorly behaved ODE. It doesn't do nice things. So we sort of invented a heuristic algorithm that basically is based on geometry, where we essentially say, okay, imagine we're sitting at some point and we're going to walk along the coastline and we're going to look back at the telescope, I mean at the lighthouse, and can we compute what our tangent angle will be and therefore the likelihood that we'll see something. So essentially we discovered it turns out the probability is proportional to the sine squared of the angle, this angle between the ray from the lighthouse and the coastline. That's just a heuristic. We will figure out why that's the case, but it's just an empirical thing that it actually works pretty well. And so from that, we can now compute the shape of the coastline. So given a coastline, given a probability distribution, we actually can get a coastline. And then we can then do that for our modified Cauchy distribution. So this is the observed coastline, the observed probability distribution, and this is what the coastline would look like that would produce that distribution. And then we can apply that back to our data and say, let's compute the coastline for these different sets of observations. And what we see is that the benign sources, the sources that we know are legitimate and doing normal things on the internet, have a coastline that's much further away from us than the malicious stuff, which is much, much closer. And the analogy I sometimes give is like, imagine you had a high-flying airplane, okay, like a commercial jetliner, and it's going across the sky, and you look, and then you look away, and you look back, you're still going to see it. It's traversing your field of view very slowly. It's not trying to hide. Versus, say, a radar-evading drone, which is just flying extremely low, and if you see it, you are never seeing it again. So surprise, surprise, people who are trying to do bad things on the internet are really trying not to be seen, and that's actually kind of their signature, right? Is if you're trying to be seen and are really bright and aren't really going anywhere, you're probably okay. But if you're trying to hide, well, that could be a problem. That's an indicator that maybe this is not good stuff. And let me just talk about finally here, and I probably am running out of time, we have seen also very interesting, like sort of pulsar-like phenomenon here, where we can look at a particular, what we're looking here is at the gray noise data over 5 years, and we can look at how many unique sources we see in a particular range coming from another set of observations that we have. Like we have essentially two different things, and this is asking the question, like, are you seeing stuff from this other location? And we see these huge spikes in traffic seen from one set of sources into this particular telescope. Now these triangles correspond to the CEO of Gray Noise tweets about, hey, we're getting these noise storms. We're just seeing all this random traffic periodically. And well, maybe it's just these particular ranges that are talking to Gray Noise. Well, this is a heat map that shows the entire internet, and you see that there are these bright bands here that correlate with these peaks. So someone is essentially blasting the entire internet, every 6 months or so. right? So this is indicative of about 10,000 sources seen by every single source on the internet, in a very short window of time. And so that's a fairly interesting phenomenon type thing. Imagine like the entire sky brightening up for a little bit and then stopping, and this happens every 6 months, right? Not exactly, but periodically. So, and then we can look at those individual noise storms, more carefully. So these are all the ranges on the internet, and essentially the black curve represents sort of like typical, like okay, in a typical month, this is how many sources would you see, and then we can look at two of these noise storms, this one and the blue one, and you can see that they're much, much brighter. They're also really different. And we can look at the equations for that and essentially say, yeah, the red one is just someone essentially made every single destination on the internet just the same value. And then another one here, which is essentially this blue one, right, is basically, it's someone basically amplified what you expected by a linear amount and then a nonlinear amount. So made the stuff that was kind of faint, increased it by a certain amount, and then the stuff that was already bright, it increased it by a nonlinear amount. So this kind of shows that there's some kind of mechanism going on here that's at the root of these phenomenon. It tells you it's not like some kind of completely random thing, that there's some kind of mechanism that's controlling these types of things. So I think what we're doing here is really advancing the science of cybersecurity. This was something that was called for in a sort of Jason's report in 2010 that said we really need to figure out how to do protocols to facilitate testing of hypotheses, establishing, what does it mean to do a reproducible measurement in the internet, continually modeling and simulating these things, and establishing interdisciplinary centers to do this kind of work. I think we're really sort of checking these boxes and really trying to set the observational foundation and scientific foundation for really observing this new domain. So I'll stop there. Hope you enjoyed the talk. I know I'm probably just right at the end of time here, but I'm happy to stay and take a few questions if people are interested. So thank you very much. I really appreciate it.
Thank you, Jeremy. Any questions here or online?
Yes.
I have a very basic question to start. When you're differentiating between benign and malignant sources, is this pre-labeled, or is this based on activity structure? I missed that. I think
So Great Noise's business is they run all these honeypots, and they have these conversations. So they'll run a web server, and then they'll see certain standard exploits, and then they'll label it. There's this whole system called CVEs, and they'll say this is this CVE. It's actually very helpful because it tells you how prevalent certain attacks are. Unfortunately, this is not data we use today when protecting ourselves. You'd think we want to protect ourselves against the most common things. So we haven't gotten there yet. Right now we just say, well, there's a vulnerability, we better just patch every computer in the world on it, even though it only has to occur if you're doing a very particular thing, right? So they provide really important data about hey, you should prioritize these things because this is everything. So for example, about 30-40% of the things you see is something called a CVE that's called Eternal Blue, right? Which has been around for a decade, which is a Windows 7 exploit. And the fact that it's still going on, and it just means you should definitely not be running Windows 7, and and if you do, you should at least be having this patch. Although if you're still running Windows 7, you're probably not patching. So yeah, so it's a very, very, it's an example of very popular thing that still goes on. With the case with CADA, you can just assume that's all malicious. No one is supposed to be talking to that network, and it's mostly two things: scanners. So things just that are scanning the entire internet. And then this thing called DDoS backscatter. So if I want to do a way I can take down your website, if I want to take down the CFA website because I was mad, because of Pluto or something, and I could basically get a lot of computers to all send requests to your website, but they spoof, but is you don't have to provide a true return address. Just like when you write mail, you can write whatever you want on the return. Well, that's the way the internet works. It's a flaw that we knew about in the 1980s. We're trying to fix it now. It's a real problem, but it is a known flaw on the internet. And so a lot of times people send the return address to the K to dark space. So they get all this, that's called DDoS backscatter. So they get to see that. So they have a lot of indication of that kind of stuff. So that's essentially all malicious. There's like, well, it can't receive anything. So it's either traffic that shouldn't be happening accidentally, but like 99.999% of it is sort of indicative of some. So we can just declare all of the CADA observations as essentially probably due to malicious activity. So that's nice. That's rare that you have just as like, this is all stuff that shouldn't be happening, right? But it's also the kind of thing that all of us would just see. It's probably like scanning and DDoS backscatter isn't just targeted at them. It's going everywhere. So we're all getting a little DDoS backscatter traffic. So it's a nice way to just get a clean observation of that stuff.
Fascinating. I have a few questions, but I'll try to boil it down to two. Well, first of all, a clarification. If I understand correctly, the data that goes into your analysis only looks at number of packets between these things. So you don't look at how long the message was, including those packets.
No, we throw all that data away. We just account the number of events. Yep.
But I feel like there's information there that you could get. So like you're counting photons, but you're not looking at what frequency they're at, or
Well, I mean, so what we do get sort of temporal information by we create these bucketed slices of a certain amount of things, and on a big center, 100,000 packets happens in a few milliseconds.
Yeah.
So those are pretty narrow temporal slices, so we can do that kind of temporal information. There's a lot of stuff, like we don't include ports, we don't include protocols, we don't consider the size of the payload,
Yeah, like there's
all
so
that
much
stuff.
information that you're just not looking at because you want like this very basic view.
Well, we want a big view,
Yeah.
right? It's about sort of looking at the largest scales over the longest time, so we need that. In addition, this is the line. You ask for one more piece of information, you're not getting it.
Oh, I see. Okay.
And that's
So
because I have lots of colleagues who are like, but I want this and I want that. And I'm like, you can have a ton of this or zero if you
Okay.
ask for it. Well, I want to see ports.
You
No,
answered my
you're not
second
gonna-
question.
Yeah,
Okay.
so this is kind of like the deal, like, when you talk to network operators, like, I can get you this, but I can't get you, like, we found that it's like a step function, like this, anonymized, and with a data sharing agreement, we can get a lot of that. Everyone's cool with sharing that. And the big problem in the internet is that we're not sharing information, so if something bad happens to someone else, like the rest of us don't benefit from that. It takes a very long time for us to do that. So yes, you can do that. I will also say, this is already hypersparse. Adding more dimensions just takes a hypersparse problem and makes it even more hypersparse. So from a mathematical perspective, we don't really gain much. Now that isn't to say there aren't sensors that are very narrow, like most of the sensors you have in your computers are collecting a lot more detailed information on this that's held locally, which, that's kind of like, okay, now we're going to do a follow-up. Like something's bad happening, these are the sources, we're going to go turn the really detailed thing on, because it's our data and we do that locally. So it's just the difference between kind of, wide area survey versus, narrow, follow-up type of analysis. So, yeah.
And let me sneak in the second part of my question, which is, it looks like you have data from 2020 and after that. And I wonder if you've seen any trends due to, say, people working from home in the pandemic, or when a certain virus spreads across the internet.
Yeah, we saw a near 20% increase in the traffic into CADA that exactly corresponded with the start of the, which is essentially, since that's all malicious traffic, not surprisingly, a lot of this malicious traffic is sort of calibrated to be a certain fraction of total traffic. So when you got the spike in total traffic, if they're like, well, our systems are set to be 0.01% of total traffic because that's how much we think we can get away with without being detected.
Okay.
It was literally like we had data in 2019 and then just, it was exactly the entire year 20% higher.
So it gets calibrated to be evasive so that...
Yeah, it's just if you're trying to, like, if you say, like, because that's a variable thing depending on where you are. Like how you only want to be a certain percentage
Okay.
of the thing, otherwise you're going to be detected. So we saw that effect right away.
Okay, we have a question here, and then we'll go online.
Yeah.
Peter?
So you fit these nice power law type models to a lot of your data, and in astrophysics, the dream is always, okay, I have a theory which can tell me why that power law exponent is 1/5 or whatever it is. A lot of yours, they change from site to site. Do you think any of those numbers have theoretical underpinnings that you could find out, or are they all just kind of empirical?
Well, hypothetically, if I wanted to find theorists who wanted to think about these problems and were comfortable with mathematics and interpreting poor observers and phenomenologists' data, I might stop by the Harvard Center of Astrophysics, right? I don't know, So the fact is, we need people who understand the theory to look into this. More broadly, I think there's a theory. You could say there's a theory of observatory science. Like we are inherently a passive activity, just as in astrophysics and astronomy is inherently a passive. Unlike our high energy physicists, they're active, right? They're we set up an experiment. We have to sort of take what nature provides us,
Yeah.
right? So we're observers, and I'd say if I wanted to create a broader observational science thing that sort of brings these worlds together, I can say on the internet side, it's $1 trillion a year activity. It seems like wouldn't it be great to figure out how to direct some of that into the more general theory of observational or observatory science that could fund observatories of all different flavors in recognizing their synergies and things. I'm always looking for a way to get more resources into basic science in order to also have people think about these problems, which are different but similar, right? It's still the same. It is, when I look at all the disciplines, this is the one that seems to feel the most right because it is inherently large scale and passive. We are passively collecting, and we're highly constrained by what we can collect. In this case for rules and societal things. In astronomy, it's just, physics just prevents us from knowing and going out and getting certain things. Wouldn't it be great if we could just go to the black hole and take a picture of it and we wouldn't have to invert all these huge, images to get that picture. So we'd love to sort of see if there's a way to create more synergistic activities between in observatory science more generally. So there's there's one more question.
Okay.
Sure.
Sorry.
Just hopping off of that, but is there a possible way to sort of develop actual experiments that would test certain hypotheses, or would that require too much organization of people to have an actual observable impact on the internet?
I mean, it's hard. It's hard, and we've even seen it's even companies that are doing this on their own networks with their own user bases have seen significant blowback when they try and do experiments.
Okay.
And so in a certain sense, you really just have to kind of observe the natural phenomenon. Now, obviously when you observe things and there's potential actions you can take, to hey, did we see this going on? We don't want that going on. Well, that's the kind of active part. And then if you make the change, and if it works, then you've sort of confirmed the theory, right? The simple fact is, one of the things we're advocating here is this faking the return address, which is called spoofing, shouldn't be happening at all. The technology for it exists in all the equipment today. It's just not turned on, and that's because it's generally perceived as just being an annoyance. Well, our results say, there's an annoyance part of this, but if someone is doing this every 6 months to essentially light up the entire internet, I don't want to find out what the true purpose of that is, right? Why don't we just turn this on, right? And so this is something we do. It's called source address validation. Network providers can do it. They just need an incentive to do it. You just have to say to them, I'm only going to do business with you if you turn on source address validation. And we're like, okay. They need 1 penny of incentive to do it, and they'll do it. But it's mostly not on. And so there's an example of where we do all these observations, we see phenomenon, and we can tell people like, this is not just an annoyance, there's actually a solution to this. So that's, and hopefully if we turn that on, like Kada goes dark. Like if spoofing got turned on broadly across the internet, I mean, its volume should drop by about a factor of 100. It should just be scanners at that point. All the DDoS backscatter should just vanish because you wouldn't be allowed to do it. You know, so yeah.
Let's go to Michael. Michael, go ahead.
Okay, I'm going to the coastline analogy. The length of a coastline or its geometry is a fractal. So when you're drawing it, you have to choose the smoothing length that you actually draw the geometry over. What's your equivalent in your analogy?
We're clearly dealing with an idealized coastline that was developed by Professor Gull, who's a professor in Scotland, who was trying to come up with some way to motivate some phenomenon that his students could understand that would produce a Cauchy distribution. So yes, so this isn't trying to be a real, this isn't like people actually use this to go and measure, it's not like, I thought it'd be like, oh, some, British navigator in the 1870s needed to solve some problem. No, it was just a toy problem that was created. So we're dealing with an idealized coastline, and we have a lot of constraints on continuity, and we are not in no way would this work with arbitrary, a whole class of arbitrary, certainly fractal things. It wouldn't work there. So it's not like real there. Now that said, one could.
It's a smoothing length. It's all it is smoothing length, which you must have equivalent for.
So you mean a smoothing length in the internet or for the actual Gull Lighthouse problem?
Well, the Gull Lighthouse problem has to have a smoothing length as well.
So it places conditions on.
I don't care about real coastlines.
So it places conditions on the derivatives, basically. So I'm sure we could say some Banach, constraint or something like that. So it places constraints on the magnitude of the derivatives, which means it's inherently not fractal. Like fractals have discontinuous derivatives. So we essentially are eliminating a fractal coastline altogether by putting constraints on the derivatives in order to make the solution. So, yeah.
So that's how you do the smoothing, is by basically forcing it to meet your criteria, which is going to be Cauchy distribution.
Yes.
Just saying.
Yeah.
Okay.
So I'll jump in real quick if you don't mind, Jeremy.
Oh, Hayden, you joined us. Fantastic. Thank
I did,
you.
yes.
So
excellent talk.
Hayden is the mathematician and the real brains of the operation. So take it away, Hayden.
Yeah, so in terms of the direction of going from a coastline to a distribution, I could see requiring some sort of smoothing depending on the kind of coastline that you're handed, in order to make it amenable to the techniques that we've used, where the distribution is going to be in terms of both the function and its derivative, for the coastline. But in the opposite direction, when we're dealing with distributions, oftentimes we're dealing with, fairly nice, smooth distributions. When we're doing the fitting to real life things, we're usually doing the fitting to something that's, going to be smooth. So in that case, the coastlines that we get as a result going that opposite direction often probably can be proved to be completely smooth every time, assuming that the PDF is smooth.
Thank you, Hayden.
Yeah.
But it is an interesting question because, again, what we're doing is we're essentially taking our low parameter fit and inverting that. We're not actually taking the true observational curve, which has these little wiggles. In fact, some of those wiggles are just like weekly, like some of those are like traffic's different on weekends versus weeks. Like I can tell you like how many weeks of some of that data is just by looking at some of these wiggles. On one of them, you'll see we separated noon and midnight because otherwise it was just fluctuating dramatically every day, right? And so it'd be interesting to think about that from a fractal perspective. And I think maybe we could relax some of these constraints on that that we have right now and be able to deal with more generalized distributions.
Okay,
Great.
let's thank again our speaker for a very interesting talk. And I will disconnect the Zoom. Thanks to everyone who joined us online. Hope you enjoyed it.
So it's supposed to be talk today.
All right.
The talk is next week.
Oh, gotcha.
Okay.
Right, so the whole purpose of this
Yeah.
was to then, so first of all, thank you so much.
Yeah,
It's a
no, of
wonderful
course.
audience,
This
and,
is,
sometimes in the intimate audience, people are more willing to ask questions.
Right.
There's probably a phenomenon there. One thing I do when I teach now, it's been really cool. I do this thing like called improv math, where I will go up and give like 5-10 minute intro
Yeah.
to like the general topic,
Mhm.
and we give the students all pieces of paper, and their job is to write down a question. And so I get, then they all, after that, they all write down a question. And then I go in the corner and I sort of group the questions, and then I give a lecture that
Oh.
answers those questions.
That's
You know.
that's pretty cool.
Yeah, no, I mean, I
Who
sort of-
came up with that idea? I've never.
It just happened to me in the middle of the night. Maybe someone's thought of it
Really?
before. Well, it was the reason it happened is like Hayden and I give a lecture on the
Sorry,
mathematics.
I'm listening. I'm just putting this away.
Give a lecture on the mathematics of big data
Yeah.
in the MIT January term every year. And, we've actually even recorded that, and there's a YouTube version of it. And I was just thinking the night before, it just seems silly that we got these students in person in this room. And I'm basically going to give the same
Yeah.
lecture that's on YouTube.
You're absolutely right.
And I just this
Yeah.
seems stupid. And I just was like, is there anything I can do? And I'm like, and it's a topic I've lectured on 1,000 times. I'm like,
Yeah.
there's no way these undergraduates are going to ask me a question that's going to be like, they're probably going to ask me some question that's going to stump me on the fly is really low. So I thought of this, and then Hayden and I did the lecture together. And on the drive over, I'm like, Hayden, I want to mix it up. And I'm sure he's like, oh God, because I have a lot of wild ideas.
What now?
Yeah, what now? Hayden's also the more
No,
skilled.
but you're absolutely right. That without interactions, then you might as well, be home or be looking at
And-
the recording.
And what's great is, and you see that the questions were fantastic. I mean, it was really good, and I actually recorded the whole thing. Like, it was in a venue that MIT has. It's like designed for robotic recording at a very high quality. And so it was a very nice quality recording. So we actually captured it and posted it. But really, what was great is I could now say I gave a lecture, and every student asked a question, and every student had a question that was directly answered by the lecturer. And those are really amazing. I also do this, I give a lot of virtual lectures, in other people's, I'll guest lecture in various classes. And usually the assignment now is, I'll have a YouTube video of the lecture. Their assignment is to watch it, and then email a question in 2 days in advance. And then I build a new custom lecture for the synchronous part that is just answering those questions, right?
Wow.
And again, it really gets over the students are terrified of being judged by their peers.
Yeah.
Here, I mean, we're all professionals, we ask questions, whatever. But the students are really terrified. They have questions, they want to answer them. The questions their peers have are probably similar to theirs. And so this sort of gives them that just enough anonymity that they feel free to do it. It also forces them to pay attention to the material, because they're like, you have to ask a question, they want to ask a reasonable question, they don't want to ask an irrelevant question. So I mean, it's something where now, and it's now something I can do, whenever I do get invited to do a talk, particularly a virtual one, I can just sort of okay, this is what we're going to do, and now it's special to you.
Don't forget that.
Oh, don't forget that.
Yeah.
No. It's not even my property.
So with regards to your paper,
oh yeah.
I mean, it would certainly be an interesting paper. I still wonder if it's appropriate for the journal, for the reason that, I mean, there's astronomy in it, right? But it's all about the analogy, and then it's more. So I'm just curious, why would you not want to publish this in an IEEE journal or one of the more?
We don't teach science to them.
Wait.
We don't teach science to cyber people. Their degrees
Yeah.
are in.
So, so you're saying this is a data science talk?
Well, I'm just saying, they wouldn't understand the analogy.
I see.
I mean, sure, we
So
published
you-
examples of little bits
Right,
of the
right, right.
analysis, but sort of pulling it together as kind of, I
they
think
would-
it's like,
They wouldn't understand the astronomy analogy, but they would understand, what you're trying to accomplish and what you get out of this.
they would,
data
but they
analysis.
wouldn't understand, they don't understand the analysis. They don't care. They just want things that like, can you help me find bad guys? You know?
Oh, really?
Yeah, they're very practical, very practical oriented. You know? It's, and so there's no, the point being that this is not new, like in any new field, like it's sort of mostly dominated by hacking and tinkering and stuff. And, the recognition that you need to observe it, and, I mean, there's like one of these observatories, CADA,
Mhm.
for the whole planet Earth.
That's it.
And they are hanging on by a thread budgetarily, right?
Who funds them?
They just piece it together. You know the way it is to try and get infrastructure funded in science.
Yeah.
They piece it together, different proposals, et cetera, say the data.
It sounds like, I don't know, NSF or DOE.
They get little bits. They get little bits. You'd think that the commercial industry would be like, it's $1 trillion cyber industry. Like, how is they can't find, $500,000 a year to, fund this
Right.
type of thing. So we're just, I just view it, I don't take it a bad way. It's just, that report, I put it there, which was done in 2010, because the question to the, do you know who the JSONs are? I don't know if you've ever
No,
heard of them.
no.
So they're kind of an elite group of American scientists, mostly physicists, who get contracted from time to time to look at hard problems for the government. They don't tend to, I'm sure you know some, but they don't tend to like
They
work
don't,
on this.
okay.
It's not like it's a secret, but they don't tend to advertise it.
Yeah.
And in 2010 or 29, they were asked to do a report, like, well, what should the science of cybersecurity be, right? And they're very accomplished scientists. They know what science is. And they well, it begins with reproducibility. You need to set up observational and measurement and analysis protocols that produce reproducible phenomenon. And whatever those reproducible phenomenon are, they are, right? The problem is it fell on deaf ears because the cybersecurity community, which was the recipient, has no training in science whatsoever. Absolutely zero. Even computer science, they don't really teach you the scientific method. It's really an engineering discipline, right? It's about the whole question engineers learn to build and scientists build to learn,
Yeah.
right? It's a very different mentality.
But I thought, people doing signal processing or, like if you develop a network, you have to be concerned with congestion and attacks and so on. And
Not really attacks. Usually you can just buy your way out of it. I mean, I know many of the leading,
yeah, no, I'm sure you do.
And they're just Jeremy,
Yeah.
and if you have a beer with them, like, Jeremy, if the bits make it to A to B every night, I sleep. And it's not my problem if if the customer's willing to pay for bad bits going over the network, who am I to interfere? Right? There's no regulatory requirement that they stop malicious activity. Right? They can be enlisted to assist, for specific events, and we try and sort of impose requirements on them. But even anti-spoofing, which has been around since it was like a flaw in the internet from the very first, and it was kind of like, well, we can't do it for the first 20 years because it was technically considered too hard. It's now standard in every equipment, right? Any of us you can turn it on in your own local Wi-Fi and just say, don't emit any packets. It's not associated, and it doesn't have a return address that's associated with this thing, right? But it's where we are, and it's a very young field, and it's just where we are in the development. And we have a lack of people in the field, and that's why I kind of, again, I was somewhat serious there. I mean, it's $1 trillion a year business, right? And to me, and sort of came to me here, it's like, the thing that connects this is observatory science. The concept of an observatory, the concept of having to passively collect,
Yeah.
not having the control.
Right.
It's not like active, most of science is active, right? Where you
Yeah,
go
in
and
physics, you have your experiments.
and you control
right there.
everything,
Yeah,
you can manipulate it. In astronomy, you have to kind of take what's given to you.
Yeah.
Yeah, and then deduce that. And so,
Okay.
but again, I'd love to figure out a way to vector some of that resource
Yeah, yeah.
into people who think about this. And so this is kind of a way to kind of begin to at least develop some mutual appreciation of the problems we have within
Yeah.
an observatory community.
Okay. I have to run to my
Yeah.
next meeting at 10:30, but maybe we can.
So I reached out to you
Follow
because
up,
I
yeah.
can't think of another journal.
Okay,
It's
so
like-
you've done your research.
Oh yeah,
It sounds like, I'm mentioning IEEE, but I don't read.
yeah, I run an
their
IEEE
journals.
conference.
Yeah,
right?
yeah,
So,
I don't,
yeah.
I don't read their journals, so I wouldn't
Yeah.
know whether it's really appropriate or not. By the way, did you park in this lot?
No, I have a Cambridge sticker, so I
Oh,
parked
oh,
a couple
okay.
blocks. You just have to get me back to that door that I came.
Let's go, that's the way to my office.
Okay.
So we're gonna go back there.
I mean, so the main thing is like, I guess the question is, we're like,